I could, reduce this noise. And then we noticed something with the piezo. It is important to the way you attach the piezo on the setup. Before it was like squeezed with some metal chuck, and there was too much pressure, so the piezo was going in a diagonal. It was not going straight. And then we put it in the new holder that Daniel received, the new holders that he made for the piezos, and it works perfectly. We ended up not using the piezo yesterday, but we attached it, we installed it, and it worked. On the range, it is supposed to work 40 to 50 microns. So that's from my side. I don't know, Ivan, if he wants to. He assembled the bath and he performed the experiment. So, Ivan, what do you say?
Ivan, do you want to explain what was good and bad yesterday?
There are a few things that Daniel and I took about the bath, because yesterday's experiment, besides that it was finally successful and we got our first publishable force trace. Besides that, we figured out a few things about the further production process. The angle of the instruments when they go down in the bath, then how to switch in between the solutions just methodically. Because actually on the way home we're discussing it with Daniel on how we can make it, and there are a few things that we can easily improve without putting too much effort, and will make this bath even more convenient to use.
Okay.
So my impression of yesterday's day and night was very positive. So,
but do you think someone without too much experience can repeat the same experiment?
Yes. So especially with those improvements that we're gonna make, this is absolutely possible. Anybody can do it.
In how long you mean?
How long you mean to improve?
No, a beginner or...
A beginner. Well, anybody who ever worked with automatic pipetteur can do it right away.
Oh yeah, it's that easy?
Yeah, 1 week.
Because, you know what, I would like to try to do it.
Yeah.
Just to...
You know, if you ever had to pipe it many times from one beaker to another.
But you have to hook the cell and...
well, you just need to be delicate. That's it. There is nothing... it's as easy as every time I cut the muscle, every time we have the cell. There is no way you can miss it. You know what? What I want to do also, this microscope, the inspection microscope that we built, in fact, when you switch to the camera, you don't lose both eyepieces. You can still see.
Yes.
You know that?
Yeah, yeah.
So what we can do, we can record a tutorial video on how to dissect a cell and attach it to the grips that I made.
Okay.
So we can do also that. And use this video as a tutorial for our...
But you know, François, I mean, from the beginning to end, you know, there is some know-how. I mean, it's not a mosquito comes out of the box and it starts producing papers, because you need to prepare the samples, and you need, you know, assuming that these students, you know, or scientists that will work with the mosquito, they have this know-how, and then you have to, you know, attach it to the mosquito, and that's sort of tedious, you know. I mean, it's a job that requires attention, you know, to attach a sample to. I didn't see Ivan how it does it. Maybe next time I'll, you know, see and take some pictures. I think it's a good idea for you to be there one day from A to Z and see how it works, to get a feel and put your hands in the process.
If I can, you know, TV, if I can record the video, because basically what happened yesterday, guys, they went for a smoke. When they came back, I already had to stop.
Sorry?
You went for a smoke, you know, and when you came back, I already had the sample attached.
Okay.
So it took to me like what, maybe 5 minutes, you know, to dissect.
Oh yeah. No, now you're very efficient with that. I mean, you know, you have the hands.
Anybody can do it. It's not something impossible. Absolutely.
Okay.
Yeah, I mean, sample preparation. You know, even Fabio using Aurora system. When you see him doing it, he's basically manipulating one single cell by hand under a microscope. Okay, so that's how he does it, and he puts it into some aluminum foil, and then he attaches it to a hook. So you know, sample preparation. I mean, that's what it is. You have to manipulate very small samples, and you need some equipment, and you need to be patient, you know, with your sample.
Yesterday, how big was the displacement?
You know that we have to look at a video for that.
You need to calibrate the camera to be able to measure the distances on the screen.
Yeah, I would say around 50 microns.
How
Because
much?
we did some experiments with the piezo before. 50 microns?
Okay.
We did some experiments with the piezo before at the same magnification. What was the magnification, Ivan? I forgot to write that. Ivan?
It was 4x. Actually, we forgot to write it down in the information file.
Yeah.
Magnification was 4x.
Okay, so I did some piezo tests at 4x with the microscope, and was around the same order of magnitude of motion. Okay, 40 to 50 microns. That's what we measured. I think.
Okay, and this was a single cell?
No, it was a group of cells.
Mhm.
You see, we work with muscle cells taken from the mouse. And the cells, mice cells are much smaller. If we had a rabbit, then I could dissect like one cell like Fabio does.
So how big was
Uh,
the group of cells, you mean?
Well, again, so in order to give you the cross-sectional area, I need to measure it on the screen. So for that, we need to calibrate the camera. But I can now give you only the number of cells, but probably 4 to 5. Because some of them, they detached, so they didn't participate in the contraction.
And
Those that
are they
didn't,
1 millimeter, like, or
I mean, long?
yeah?
Yeah, maybe, yeah. But
1 millimeter long?
I don't know. I don't remember the. Well, yeah, roughly 1 millimeter, maybe more. But the width, the thickness of the sample that we had, we need to measure. I don't know. It could be like I don't know, maybe 300 microns, something like that. All in all,
Okay.
I'm not sure. You need to measure.
You mean the thickness of the sample? You mean, Ivan, it was 300 microns?
The cross-sectional area, yeah.
The cross-section area, but and the length you say that was like roughly around 1 millimeter.
Maybe 1.5 millimeter.
Yeah. I was very surprised, Francois. We did 7 runs in all, and this was the last shot, and we improved every shot we did. Every run we did was better and better and better and better. I think that next time we go there, yeah, this is another thing I wanted to say is the sample. You know, chemical activation is so predictable. It's so easy. You just go in the fridge, defrost the sample, and there you go. You put it there and it contracts. You know, so you eliminate all these uncertainty with live muscles. You know, for electrical stimulation. But we need to master that too. You know, it adds a bit more complexity for sample preparation and sample, preservation.
Yeah, but if we master one, maybe it's enough because the people will master whatever they want, and
I think this is a very good strategical decision to go to a sample which is highly predictable. So you want to test something on the mosquito with a biological sample, you just go there and you do it. You know, you don't have this frustration. The sample didn't work today. This was not good. And then you lose time, you waste time, and you build on frustration. I think this is a nice decision. You know, let's go for something that we can control, okay? And then we get forces in the order of what people will get. So now you're using the mosquito in a real case situation, okay? And then if people want to switch to other experiments which are more complex, that's fine. But we already know how the mosquito performs. We know how to tune it. You know how to optimize it, and you know. I think for the optimization and characterization, it's huge. It's really good.
Okay.
And this is data that you can. I mean, this is publishable data. You know, this is real. I was very surprised to look at this last shot, to see it perfect. You know, plateau which is almost you know, flat, and you see activation, disactivation.
Yeah. Do you think you can publish that?
In the technical picture.
Okay.
Well, it doesn't have scientific merit, but that's, you know, if I can show you the trace that we published with Dilson.
So basically, it's not the biological paper. It's the paper about the technology in the journal for engineers, like the one that we published with Alex Labuda. It was a review of scientific instruments.
Mm-hmm.
And just to give an example of what can be done with this system, we provided the trace of the forest development, you know, recorded at Wilson's place. So for our this particular experiment, we can describe like briefly in 2 pages the setup that we used, including the mosquito shrinking shrinking tube sensor, then the acquisition system, like the laser and the detector and everything, the electronics, put nice principal drafts that Daniel can make for us. And at the end, we provide this graph, the trace of the force development, saying that this device has been used once in the biological experiment, and this is the typical trace of force that you can record with it.
It's people.
Yeah, so if you go on, I just put the link there. If you go on page, which page is this? 1, 2, 3. If you go on page 3, you see the trace that we. So you basically, this is the technical paper, right? You see a technical description of the device, some pictures showing the optical layout and how it's made, and 1 trace.
Yes.
Okay, on page 3, and what you see there in the middle, that's because we moved the piezo during the plateau.
Mm-hmm.
And even in the case of this penguin system, okay, you can see right before the contraction, which is the activation, you see a small dip. Well, that dip is because you're changing solutions.
Yes.
This is optical artifact. You know,
This is a, yes, that's because of the change of solutions, and you should have another one right before the relaxation, which you don't see in this picture. I don't know why. Sometimes you see it more, sometimes you see it less. But I think we can optimize activation, chemical activation with this new bath. You know, adding 2 holes and timing between, you know, sucking a solution and putting the other one in. I think you can really optimize that to reduce this noise. And if you look at our trace already, in the later part, where it's before relaxation, okay, that signal that comes from changing solution is smaller than the one that comes from in the beginning before the activation, right? If you look at the trace, that signal is a lot smaller. So I'm very confident that that's Ivan, you know, changing its pipettes, you know, and injecting, you know, faster or slower or whatever, you know, it does that manually. But because we got this good solution exchange before the relaxation, I'm confident that we can make that a standard, you know, and even improve it a little bit.
Okay.
Yeah, so this technical paper is very important for something new like our technology.
Yes.
And I would say that every time we bring a new transducer, new type of transducer to fields, and record something like this, for every type of transducer, we can publish a different paper.
Mm-hmm.
So basically, just to point this, okay, so this one is the shrinking tube type. Okay. Now, say we bring like the one that is based on the blue.
Mhm.
Next time we bring something from Maxim, and this is the intrinsic potential.
Yeah.
So and then it's like this paper. It's like 2 pages, not more.
Yeah.
Just the leaf.
Yeah, you can definitely write a white paper, right now.
Well, but I mean, yeah, you can, but we need publications, And this paper, like in the Review of Scientific Instruments, it was very easy to publish because it's absolutely straightforward and there's nothing to, really discuss.
Yeah. So we need to think about how to leverage this data, because now and we can produce this data, we can reproduce it quite easily. It's I think from now on it's just a matter of optimization, having better transducers of different types. So it's just increasing precision, and Ivan is gonna get better and better with how to set up everything. Eventually, he's gonna write a protocol, which will be the manual of the mosquito that will go to. Maybe Ivan should think about that, as you improve your practice, maybe you should deposit some of this uh, on a mosquito manual. You see?
User guide.
Yeah, definitely. No, I'm gonna take the notes for sure, like the guide for the user for sure.
Exactly. How to do stuff with pictures and maybe a video or two, or
You know what? The main trick here, like I was struggling against the noise when you switch to the relaxing solution, because when you activate whatever the noise you create putting the activating solution, it stays. You leave it behind the trace of interest. Okay, so after you change the solution, like this noise, it happens, and then after the cell starts to activate, so whatever happened before this noise, you can simply cut it off. But then you need to switch back to the relaxation. And this noise will be right in the middle of your plateau, or like at the end of your plateau. So this is the tricky point, like how to diminish this noise. So the trick here is to work in the nice pace. You don't have to rush, like you do it slowly, like you pump out slowly and put the new one slowly. And then the noise will be acceptable. So this is the main trick. And what we figured out, like, that if I had 2 channels, because I used one for both, okay? But if I had 2, and if I put both pipeters at the same time and keep them like this, so one I used to pump out, and simultaneously, almost simultaneously, I filled it up with the new solution, that would be the smoothest curve.
And you maintain the same level.
Well, more or less, yeah. Plus, like on the way back home yesterday, we spoke to Daniel, like, in case if you want to control the timing precisely, maybe we can simply leave these outlets for the manual pipettes and have the place for the barb feeding to connect to the pump. There are pumps, the Phil has one like that actually.
Peristaltic pump?
Yeah, like, it's not peristaltic, but you put syringe inside, so it can push one solution and suck out that simultaneously.
Actually, I think Phil has one. Phil has a pump like that.
Yeah. I don't know if he uses it, but he has one for sure. So
yeah,
we can simply make just an outlet for this type of pump, and basically we delegate to our future clients that in case if you don't want to do it manually, you need to control the time precisely, then you simply connect our bath to this pump. So we can do that. But
yeah, it has an RS-232 input output, so
because you see, for general needs you can do it manually, but sometimes some studies they require precision in the time.
Mm-hmm.
So for that it's hard to do it manually.
Okay.
So then
do we move to the next one?
Yeah.
Okay. Bill, do you want to go on to start your?
Well, I've been working on the modeling in MATLAB.
Ooh.
It's not finished yet, but it's coming along. I can quickly show you if you want. I'm building some interactivity into it right now, but like right now I can sort of see an image. I haven't done the calculations of the actual percentage of overlaps and things like that, which could be interesting later on, but that'll come soon enough. I have formulas for that already. I mean, when I say that, I mean like the reflected light, how much is overlapped onto the receivers and things like that. Right now, I'm using just the configuration of 3 receiving fibers and 1 emitting, but that could be changed. So let me just see if I can call up an image here for you guys. I sent some pictures to you, though. You saw like
Yeah.
the models that I was thinking of.
Mm-hmm.
Just give me a second there. Let me see.
So is your model done to make calculations when we have some parameters to enter in?
Yeah, like it's the way it's working is you enter how much bend there is, I guess.
Okay.
You enter the angle of the bend, and I'll explain a couple quickly what these are. And you enter like the cone of the light, So these are like 3 input parameters. And from there, it will produce the intersections of the light with the fibers.
Wow.
But of course, like in the future, if you want to model something, in the future, what happens is actually it's the reverse that needs to happen. It's that we need to first determine how much light is falling on the fibers, and then work backwards to sort of calculate the position, So here, right now, we determine a position, and then we see what kind of light hits the fibers. Whereas later on, we have some light hitting the fibers, and then we work backwards to see what the position is,
Okay.
But let me see if I can share this. Share. Excuse my computer is a bit slow. All right, just a second here.
Hey, Jonathan is doing the 3D piezo. Wow, this is really cool, man. 3 axis. Nice.
Can you guys see anything?
That's
you see-
$1,000 of parts.
Oh shit! $1,000, man. How much you wanna
You
sell
just-
that?
50,000.
But they,
I can't see, Bill. It's a black screen.
See anything? Do you?
On my side is a black screen. But he's saying that he's thinking.
No. It's a rendering window though. Maybe there's like driver issues with the rendering engine or something.
Okay.
If you try and screen share your desktop rather than the window, it might work.
Screen share my whole desktop.
You get that?
Yeah, yeah.
Well,
Rather than
let me
just
try.
the window.
Yeah, okay, let me try. Screen. Right, screen share. So, you see
Yeah,
anything there?
yeah, it works.
Okay.
We see a
All right.
cone
So,
and 2 plans.
yeah, that's right. So let me just zoom out, and yeah, so it's a cube of space here. You see this red, I don't know if you can follow my cursor, but there's a red curve.
Yeah, yeah, I can see it. Yeah, I can see, of course.
The red curve is, yeah. So the blue plane, you have to imagine, is the plane of the fibers.
Mm-hmm.
The green plane is the mirror plane.
Okay.
All right, and initially there's no bend; they're parallel. But when there's a bend, they deflect, and then you have this situation. All right, let me just zoom in a bit. You can see a big red circle on the blue plane.
Yeah.
This represents the arm, the cross section of the arm. I just assume it's a cylinder for the time being.
Yes.
And and you can see 3 small circles on top of the big circle there on the plane.
Yes.
And those are the receiving fibers. Let me see if I can zoom in on those. Again, slow computer, sorry about that. Yeah, so you see that the cone comes out of the center. That's the emitting cone. And there's a red dotted line going up, hitting the plane and bouncing back in a green line.
Oh, okay. So then you have the projection of that.
That's the reflection, you know, of the center of the cone.
Yeah.
So then I have like some points that are on the green plane. You can see some cyan or blue, light blue, and a yellow and a red.
Mm-hmm.
And those are then reflected back onto the blue plane, those points. Those represent the ellipse that results. Those are the major and minor axes of the ellipse that results from the, you know what I mean?
Yeah.
Yeah, and then they fall back on the blue,
Layer.
plane there, but
But-
much bigger, of course. So
Yeah,
you
but-
can see that this is a cone now with a half angle of 30 degrees. So the cone is 60 degrees across, you know?
Okay.
Mm-hmm.
Apparently, Jonathan told me this is what the fibers put out. This is crazy, you know what I mean? That's a very fat cone. It's not very useful, in other words.
The glass fiber.
So,
Can you hear me, Bill?
yeah,
The glass fiber.
yeah, go on.
Half the size.
Half the size?
Yeah. So
All right, so I can change that. Give me a second. I'll just re-render.
But you can also change the distance between the two planes, right?
Yeah, all that is parameters that I can set, and when I enter some, when I make it a little more interactive, what's going to happen is going to be like live time with sliders, you know, with slider controls.
Okay,
You
so
can,
you're gonna make it gooey.
Yeah, you can change the cone, you can change, and I'll also build in like to calculate the actual overlaps. And later on, like if the light isn't uniform, but it comes in sync waves or I don't know what, the intensity is not uniform, you know, that too can be built in, and then you can have all kinds of, which raises a whole ton of problems if that's the case.
Wow.
Because then there's no single solution. Like when I was saying about working backwards, the amount of light that hits a fiber is not necessarily unique. It may correspond to several possibilities. I don't know if it's a one-to-one situation. You understand what I'm saying? Like, if you can, from the information on the fibers, work back to deduce the position of the arm or the bend. You know what I mean? But that's something we'll have to investigate.
Okay.
So let me see here. The Jonathan said it was half. Let's make it more interesting. I'll put a very small angle here. I'm at so much delay here, it's crazy. And I'll change the angle there is 0. Right, bend radius 30. I can make a smaller bend, I guess, by increasing the bend radius.
Okay.
All right, so I run this.
Is that the
See if you can.
centimeters, Bill?
I'm sorry, I can't hear you, man.
100 is centimeters or what?
All these are millimeters, 100 millimeters, I guess. So what that means is that when you bend, it's like you make a circle, you know? I mean, a straight line has a radius of infinity, so there's no bend in a straight line, you know?
Yeah.
When the arm is straight. When you bend the arm, then you can imagine that there's a center somewhere around which your arm is bending.
Yeah.
And that distance from that center to the axis of the arm is the bend radius, you know? In any case, so here there's a very small cone now.
Mm-hmm.
And you can see that, you know, the light comes back and lands on 2 of the circles, and one of them is cut there. You can see, right now all I can do is plot the points, the blue and red and yellow points that represent the ellipse there.
Okay.
But in the near future, I'll have a nice ellipse drawn on that plane, you know?
So these blue points are
So anyway, that's
the
part.
limit.
I'm sorry.
These blue points are the limit of the ellipse.
Yeah, you can see that. Yeah, like the cone comes from an apex. All right. The peak of the cone is the apex. Up here, a blue point floating in space is the reflection of the apex in this green plane. So you can imagine that this apex up here, the reflection, goes down through the yellow point in the green plane and casts an image down onto the blue plane.
Yeah.
In the end, what you want is the ellipse on the blue plane.
Yes.
And how much it covers those 3 red circles.
Mm-hmm.
But
You know what I mean?
Yeah. I fully agree.
It's
It's not at scale.
All this is scale. Right now we're seeing just a skewed view because we're on the side. If I rotate a bit.
But I mean, are these fibers the 1 millimeter?
Absolutely. Yes, these are supposedly 1 millimeter. Yeah. I'm using real numbers here.
And also for the beam and the angle.
I'm sorry. The what?
The angle you put for the beam, how much is it? Or in percentage of the deflection? Zoo asks for 1%. Is it what you have?
He wants to be able to detect a 1% deflection.
Yeah.
So is it what you have?
Right. Sorry for interrupting. Well, look, I mean, the numbers are all there. It's just a question of I've put it in maybe in terms of a bend radius or something, but we can change that to percentage and then go from there.
Okay.
But right now, I'm just nailing down the mechanics and trying to make it a little user friendly.
Yeah, Bill, leave it in band radius because everybody speaks in band radius, and we'll do the calculations. In percent.
Well, whatever. I mean,
whatever.
Yeah, you can have.
But the gap here, D, is huge there. No?
Yeah. Okay. So we can make it smaller.
Can you share the code?
I'm sorry. Yeah, you want to run it over there?
Yeah.
Yeah, I'll email it to you. It's very. It's not that big, but I can email it right now. Actually, maybe you can run it over there and get a better appreciation for it.
Excellent.
Why don't we do that? Actually,
can you
that's
tell
a good
me
idea.
The length of the gap?
Yeah, I'll tell you right now. In those images, what I was assuming. Give me a second here. I was assuming kind of a, let me see, a 5 millimeter distance between the mirror and the receiver emitter plane.
Okay, and it's a flat mirror?
Yeah, I'm assuming a flat mirror.
Oh, that's huge, Bill. According to my experiments, that's huge. I was
5
very
millimeter
close.
distance. Yeah, well.
In order to see
Whatever.
the
So tell
crossing
me
of,
what it should be.
in order to see the crossing of the signals, the video that I showed, I think I was at 1 millimeter away from the fibers.
All right, so there you go.
But don't forget,
1
wait a
millimeter.
second. Don't forget, my situation was a little different because I had a 1 millimeter fiber in the middle too.
Yes, it's very different.
Right.
Okay. It's
All
very
this
different.
can be, it's a simulation, so we can do whatever the hell we want in about 2 seconds. You know what I mean? So
But in
Yeah.
your,
Okay.
the
Perfect,
structure
yeah.
is here.
in your
So I'm just gonna email this right now to you.
okay.
Actually, you can change topics, talk about something else. I will stop my screen share. I'll email it to Jonathan, and he can run it on MATLAB over there.
Okay, it's very nice, Bill. Thank you.
Very nice.
I think it is very nice, and we're discovering another resource within the network that, I started to play with MATLAB, and I did maybe a month, and then I got fed up, because my mind is with graphical programming. I'm a visual guy. I can't stand text programming. You know, my brain doesn't work like that. So
It's the only way to program.
Was.
hey, that was
Anyway.
before, man.
I love MATLAB, so it's really cool. I had a lot of fun doing this, actually.
Yeah, this is really nice. So
Does
I
it
really
take
appreciate.
a strong computer?
No. No, it's just the lag of our, you know, the Google chat gizmo that we're using here really sucks the juice on my old computer here. So
Okay.
yeah, don't worry about it.
Oh, that's very nice, Bill. Thank you.
Thanks.
And in your model, it seems to work.
Pardon me?
In your model, it's working. We have the ellipse
Yeah.
coming back to the 3 fibers, and 1 fiber is incompletely covered. Is it right?
Yeah, so what I'm thinking of doing is to, you know, make, you know, display, let's say, there's also some light that's lost that doesn't fall on anybody. So you can calculate all these things and, you know, decide, say something about it. I don't know.
And you can put a Gaussian beam or something like that. You can put a structure to your beam.
The way I'm thinking is that this cone of light, I have it coming out uniformly. I don't know what it means in terms of intensity, though. Right now, we're just playing with ellipses and circles intersecting in a plane.
Yeah, so you're assuming a flat top beam.
Yeah, so you know, if you want to give them some weight now,
yeah,
and that there's more intensity here and distributed in a sync or Gaussian or I don't know what fashion, and then you can do, you know, let MATLAB do the math, and have a final, let's say, intensity, or I don't know what quantities you'll be chasing, you know?
Yeah. Perfect, man.
Yeah.
This is really cool. It's really cool because it has a lot of potential to be applied to, I mean, the MATLAB simulation, you know, to be applied to other things.
Yeah.
And that's a skill that people need, you know, when you sell an instrument. The idea is basically to sell solutions. Yeah. And some people have models, you know, that they want to fit with their data. And I did that a bit in my LabVIEW program. I have different models that I can fit rapidly, but LabVIEW is very good for running hardware, okay, to interface with hardware, but it's not as good as MATLAB, you know, to do the maths, to do the fittings, to do the simulations, to do all these things, okay? So what people do, they actually, because MATLAB and LabVIEW, you know, there are two companies now that they realize their complementarity and they work together. So you can basically have a code written in MATLAB and just copy and paste it in LabVIEW, and make it as a function, okay, that you just plug into a LabVIEW code. You see? So
nobody steps on anybody's toes, right?
Yeah. But this is very powerful because now you have a program that you can use to you know, talk to machines and then use to process data. And as you sell solutions to people, you know, some people might say, hey, I have this model, you know, I would like to, this is what I'm playing with, you know, so can you have the mosquito program, you know, incorporated into it? And this is extremely powerful. I mean, yesterday, if we got these results fast, it's because I have a huge LabVIEW background with me that I'm bringing in Fields Lab. So yeah, right away I can get the data, I can condition the data, I can do, you know, all sorts of things, I can do analysis, and I have this program for visualization, I synchronize it with the video, you know. So all these tools are there, which allow a very rapid, how do you say, very rapid loop. You know, you get the data, put it into the model, and right away you have something meaningful within seconds.
Prototyping, like.
You see? Yeah. So that's why it's powerful to have MATLAB with LabVIEW working together, because you give people a very complete solution. You say, hey, you align your thing, you get your data, and within seconds, you know exactly what kind of information that data contains because you run it through your model.
The other nice thing you can do with MATLAB is upload the algorithms onto a chip or an FPGA.
Yeah.
So you can do a total hardware solution with no computer required.
Exactly.
And have a display saying newtons of force. and that's it.
That's cool, man.
Yeah.
Or angle displacement.
So, Jonathan, I've sent it, and if you want to run it, go for it.
So what?
Anyway, it's a work in progress.
The power supply is $248.
Power supply? What?
Okay. Can you put a link in there or?
What?
A link to what?
The power supply? Because I need to buy it.
Yeah.
This is the high current, high power one. It's 26 kilos. And it's about $248.
26 kilos. You mean kilos what?
Kilograms. Yeah, because it's 30 amps. The melt glass.
So the shipping is.
Yeah.
That'll run your hair dryer.
Yeah, the other one, it should be around $150 max for shipping. FedEx. 150.
I don't. Yeah.
And it's
Okay, you put the link.
$248.
It's very.
Yeah.
Something
Okay, power
else.
supply.
Yeah, she's looking for one that would be good for muscle activation. So, bipolar 150 volts at 1 amp. Both power supplies, or all power supplies I'm looking at, are USB controlled.
Oh, nice. So this one is USB controlled.
Yes,
So it's 30 amperes, 30 volts.
correct.
Perfect. All right. So $250, man. That's a good price.
Plus shipping.
I was ready to spend 500 on a power supply.
Yeah.
On a good one, and it's USB. So this is the same company that does the one that we have, right?
No. They all look the same. It's one
They all
box.
look the same.
Yeah.
Yeah. Okay. Chinese
Uh,
are very open source.
She has a 30 volt, 3 amp one, $93, $63 shipping, with a USB port as well.
Okay.
So if we want a lower power one,
And lighter.
and it's 6 kilos.
But now we need to talk to Ivan because we still don't know these parameters for. I think we need to hold on the other one because we still don't know these parameters for activation. You know,
Yeah,
Ivan has to redesign.
he informed me on the specifications.
Sorry, I'm not in the loop.
He showed me the gold standard, and I copied its specs.
Okay.
You mean the stimulator?
Yeah.
Yeah, okay. I sent the information to Jonathan. The ranges.
But are you comfortable with these parameters? Do you want to wait until we do some experiments at Phil's lab before?
Well, you see, the problem at Phil's lab is that they don't have any stimulator whatsoever. They borrow one from whatever lab, and it's more powerful than what James uses. But
Yeah.
we still we haven't tested it yet. So I'm gonna fix the bath, and we see if that stimulator from Ion Optics that Phil brought from his friends is good enough. Because its abilities is like they are within the range of what we can use, but normally, like the big lab stimulators, like for example from Grass that I sent to Jonathan, they can do much more than what this one can. So we will try it first, and then let's see.
Okay, so I would like to be kept in the loop because I was there to make the program for James okay, to activate the cells. And I made a stimulated program, so I know what kind of voltages he wants and how he wants to arrange them. He has the bipolar voltage thing. You need to adjust the time the voltage stays high and the time the voltage stays low. So I want to make sure that this machine has these capabilities of adjusting these parameters, and I want to make sure that I could actually do it fast. Using my LabVIEW programs. Control it and make sure that it does what we need to do. Because you can take something that takes more time to integrate it into the whole system, and then because you lose time, you lose money, right? So I want to see if we can fast.
Okay, you know what we can do? Next time when we go there, like for example, tomorrow, I was planning to go to Pilsen. And we can ask James to bring this stimulator back in the lab. Or what also can be done is we can write him an email and ask to give us the name of this stimulator.
Yeah.
We can find the specs online. It's the one.
But that's not good, Ivan, because that one there you can control by computer. That one there. If you remember, it has some preset functions.
Yeah.
Right.
Yeah. So I can tell you now that this is the stimulator from Ion Optics.
Okay.
Maybe but if you can come see tomorrow, we can ask James to bring it, so you can read all the parameters and see if you can program it.
Because there are two aspects here, right? It's one of them is parameters, which you know from scientific literature and from your experience, and the other one is automation and integration.
Yeah.
Okay, which I know and I want to see. To make it versatile, so that and to make it plug into the rest of the system. Okay, so the idea is to put everything in a suitcase. You have a LabVIEW program that runs your piezo, runs your mosquito, runs your stages, whatever, and it also runs your simulation, and you have all in one. You see? Okay.
Yeah, so I'm gonna write an email to James. I'm gonna ask him to bring it.
Okay. Perfect.
Okay. More recent discoveries or not?
Hmm?
Oh yeah, actually, you know what, TV? I found it right away.
The circulator does nothing. That's our recent discovery of the day.
You're testing the circulator?
Yeah.
Well, we problem is that we test too many things at the same time, but it doesn't seem to work better
according to the specs.
than the Y junction.
According to the specs.
Well, just compared to the Y junction, it doesn't make any difference.
Guys, I just sent you the link to the stimulator that I found it right away.
Okay.
They have PDF file on the webpage, so maybe it has all the information.
Okay, can we stop the meeting?
Yeah, I'll go with those software.
François, can we? You want to say something about optical fiber coating and new transducers?
Well, I tested one because the other ones are glued and they are not dry. And surprisingly, I don't see in the new Chinese mosquito, I don't have good results. So I will continue playing with it just to understand more.
What kind of results you're looking for?
Well, more sensitivity compared to the other transducers. I see there is more light coming back to the than before, but I don't see more sensitivity. So I don't know. Is it more light creates more noise or what?
The mirror has to get better. Quality goes down.
Should I decrease the gain?
Okay, so first thing you say, the mirror looks better because you receive more lights when you compare it with other mirrors.
Yeah. So I compare with an industrial mirror, and this is my maximum. I compare with the new transducers, and I see more light than with the old transducers.
Yeah.
So only thing I'm sure about.
What do you think about the test I told you with a very small disc of glass?
Yeah.
Okay, Ivan.
Yes.
Ivan, you remember yesterday I went on the shelf at Fields and I was looking at some discs of glass, very small, tiny.
Yes.
You remember? And they're cover slips. They're very small. And you said, if you want, take the square one. You remember?
Yes.
Okay. Can you ask Phil if he can give us like 10 of these? Maybe just for a trial, and then if we really like it, we can buy a whole set. But just to try, because what I'm thinking of is Francois to use different coding techniques, and have some mirrors on these things, and then use a laser pointer and the power source that Jonathan bought to compare different coding techniques in terms of intensity reflected and transmitted.
Okay, so you want to borrow a few cover slips, round ones, right?
Yeah.
Okay, I think I will ask. Shouldn't be a problem. I will ask.
Okay. Because I can set this up for you, Francois. I can do the optical assembly. We never use the power meter that Jonathan bought, so I'm really happy to to play with it. And we'll use a laser pointer, the red one, or Jonathan has green ones. We can set it up on a platform, and you just put your sample there and measure the reflected and the transmitted power. So now you'll have a tool to quantify the properties of your coating in transmission and in reflection.
Yeah.
And I think this is because we only have subjective estimations of how good the coating is.
Yes.
Okay.
With the mosquito plug, I can see there is more light coming in.
Okay. But is that with through a gap or is through no gap? It's just it's not through a gap. When you say more light coming in, there is no gap. It's just the mirror on a fiber. That's it.
No, it's connectorized.
Okay, because there you see, when you do that now, you add other variables. It's what is the length of your gap.
I did the same before connectorizing, just aligning the lever and the delivery fiber.
Okay.
With a removal connector.
Yeah.
And you see a lot of light. You can adjust the gap. You see a lot of light coming back.
Yeah, I also think that noise. It's not actually not noise, but it's these interference signals that you get. And maybe we should try the angle, delivery fiber.
Yeah. So I try to cut with an angle using the cleaver.
Yes.
And the old cleaver we have doesn't cut well because I think the blade is bad now. It breaks, it makes debris. And the FIS cleaver, the new one, when I try to not to align the fiber or to put an angle, it also the same makes some chips on the fiber.
Yes. Yeah. Should we buy a new one, 8 degree or? Maybe we should play with it a little bit. Huh? I'll play with it a little bit. Maybe I'll find the way to.
Yes. We should
Or maybe
do-
maybe we can buy the small one only. You know.
maybe Maxime or someone has one.
Oh yeah. That's a good idea. Yeah. Okay. Yeah. Okay, guys. So
Do you need the mosquito demo at Teams or not?
No, I don't have.
No.
Bring it.
no, was there just as a backup.
So yeah, please bring it back. So
Do you need it today?
Well,
Because I can go today. I need to bring the back.
yeah, but it's already 4, so you won't be back.
Yeah, I can. A couple of hours.
Yeah, bring it, please. Yeah, for next time. Okay, so we can end this meeting. Thank you.
Thank you very much.
Alright.
So, who's coming tonight? Jonathan, Ivan, Bill.
Coming to
François?
what? What's going on?
Coming where?
To Café Artère, 6 o'clock. Meeting with Communautique and Ecofab.
Yeah, I said I would go. I would prefer, actually, I don't want too much to go, but if I don't go, they may find it weird, no?
I think you guys should go for. Well, I don't see. I can't go because I have to work somewhere else.
Okay.
But it's all in French, right? So
Yeah.
you should guys probably go. It's more useful.
Okay.
Yeah, François, I think it's good to show up just at least half an hour.
Yeah, I'll try not to stay too long, but
Okay. Perfect.
TV, are you gonna come in the office?
It's 4:20. If François goes there, I can come to the office and then we both move to Café Artère.
Yeah, then I'll wait for you, okay? Because I had to I wanted to talk to you about the thing that I asked you.
Yeah. Okay. Perfect.
Okay, so I'll wait for you.
Yeah. Okay.
So sorry, TB, you go directly there or you pass by the lab?
I'll pass by the lab.
Okay. See you.
All right.
What time?
I'm getting dressed and then I go.
Okay. See you soon.
Okay. Bye, guys.
Bye.
Bye.